Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Applied Thermodynamics, Module 5, Refrigeration and Air Conditioning System. Till this point of time, we have covered the concepts of refrigeration, that is vapor compression system and vapor absorption systems. Side by side we discussed about refrigerants, and then we started with air conditioning systems. So, in the first lecture we covered the fundamentals of psychromatics, which is a very important concept in air conditioning systems, where we deal with moist air and its properties. Now, in today's class we will be discussing about air conditioning processes, and moreover our attempt would be to discuss about the thermodynamic aspects of all air conditioning processes, and side by side we will try to see that how the moist air properties is going for a change for the requirement of air conditioning systems. So, if you actually think about air conditioning processes, there are 4 fundamental processes: dehumidification processes, humidification processes, evaporative cooling and adiabatic mixing of moist air stream. And I mentioned in my earlier lectures that when you deal with air conditioning processes, try to control simultaneously temperature as well as humidity. Now, another aspect is that while controlling humidity, side by side there is a possibility that temperatures can increase or decrease. So, basically when we deal with humidification processes, our main intention is to remove moisture from the air, and when we do humidification processes, that means we add moisture in the air. So, in the process either you have to add steam or you have to use water, and since there is a variation in temperatures of air and water, in the on the name of increasing dehumidification or humidifications, there is also possibility that temperature also is going to change. So, in that sense the humidification and dehumidification processes always involves heating or cooling coils depending on the requirement. So, basically it is a dehumidification with heating or dehumidification or cooling, or humidification with heating or humidification of the cooling. So, this comes in a single go when you deal with humidification or dehumidification processes. Another important aspect is the evaporative cooling. This evaporative cooling process is nothing but which is similar to adiabatic saturation processes. In the last segment of air conditioning processes, it could be adiabatic of mixing of two air streams. So, prior to this in our basic thermodynamics, we all deal with there are two air streams they try to mix, or there may be multiple air streams and they try to mix, and when they after mixing they go as a single entity, and through these processes there are various changes in the properties of air. But here this mixing will be mainly focusing for moist air streams. When you deal with moist air streams, that means we have to deal dry air as well as water vapors simultaneously. Okay. Till this point of time we have discussed about many we have discussed exhaustively what is a moist air, what are the different processes, humidifications, humidity ratio, what are the moist air and what are its different properties. By properties I mean temperatures. Here temperature could be a dry bulb, wet bulb or dew point temperatures. Then we also have humidity ratio, we also know relative humidity, and side by side other properties like enthalpy, entropy can be calculated. And while dealing this calculation processes, we also have introduced a chart which we call as a psychromatic chart. In fact, this psychromatic chart is the backbone of air conditioning systems, because this particular chart gives all information which is required for a moist air in a common applications. So, in the single chart will give you the properties directly, like wet bulb temperature, dye bulb temperature, specific volume, enthalpy, humidity ratio, relative humidity we have discussed so far. So, I am not going into deep into details, but these are very much required to study or to understand the different air conditioning processes. Now, when we start these air conditioning processes, we start with basic energy balance equations. Of course, we have mass balance equations. When I talk about mass, there are two possible masses, one is mass of air and one is other is mass of vapor. So, what we will actually look at this, that the analysis of air conditioning processes is governed by conservation of mass and energy principles for dry air as well as water vapors. So, for example, if you talk about a domain in which the moist air enters, and also in some segment or some exit location the moist air goes out of the domain, and we choose a control volume. So, there is the possibility of heat interaction. Of course, we do not deal about work interaction here too much. So, there could be a possibility of heat interaction, but if you take adiabatic systems, this heat interaction is not allowed. And of course, when also and most of the situations, when you change the properties of moist air, the water is used, either water is removed from the air or water is sprayed into the air, or air comes into contact with water so as to increase the humidity, or in some way that your mass of water vapor will keep on increasing or decreasing. So, to analyze such systems, we consider there are three different states, 1, 2 and 3. 1 is inlet state, 2 is exit state. Always we use this terminology, 1 and 2 are inlet and exit state, and 3 will always be either adding mass or water into the system or take out of the systems. Heat transfer can occur in the certain volume to the surroundings, depending upon the application. It can be positive, negative or 0. So, for a very general domain, one can use this mass and energy balance equations in a steady flow situations. First thing, we talk about mass balance. Typically, when you talk about mass moist air and you deal with air part, the air part do not change. So, m dot A is equal to m dot A 1 is equal to m dot A 2 is equal to m A. But what changes is the addition of water, and when you add water, the water vapor or mass of vapor increases. So, the mass of water vapor changes, and this mass of water vapor, from the basic definition we can bring humidity ratio into account. So, through this humidity ratio omega, we can correlate the relation between mass of water vapor and mass of dry air. So, likewise we can frame a mass balance equations. The amount of mass which is getting added into the system is equal to m dot A into omega 2 minus omega 1. Omega 2 and omega 1 is nothing but the humidity ratio at the exit and at the inlet. So, at the inlet it is omega 1 and at the exit it is omega 2, and then we can also write down the energy balance equations. So, energy balance equations takes into account for the fact that what are the energy interactions possible. First is QCV, that means heat addition or control volume heat that gets added here, and one part that comes from the inlet, because if you see there are two inlets, one for the moist air inlet that at state 1, other is moist air inlet at the state 3 in the form of water. So, when you multiply its mass with their specific enthalpy, we can get the total energy, and the energy that leaves is through this exit stream, and this is here and gives is as a negative sign. Now, here we can simplify these equations by considering this omega, bringing omega 1 and omega 2 into picture, and ultimately we can frame a very common equations where which is a energy balance equations, and here this energy balance equation has basically four parts. One is QCV that gets added into the system, other is the part, and here entire thing that goes common is the mass of air, dry air, and that is the very basic, because this particular thing, the part does not change in the entire system. Mass flow rate of dry air does not change, and this contribution of this mass flow air, when it has two aspects. One is through the process of changing, there is also temperature change. So, the change due to energy that gets added through air only. Other part is the through for the water vapors, when we multiply this with m dot A with omega, we get in the form of the energy associated with water vapor. Here G stands for the gas phase for the state 1 and state 2, and the difference in the humidity ratio when it multiplied by enthalpy of water, because this is in water form. So, you have to calculate the enthalpy at that state. So, enthalpy must be calculated at temperature which is available at state 3. So, this is the very basic equations that we are going to use for all fundamental air conditioning processes which we will be dealing now. And the first fundamental processes is the dehumidification process. So, when a moist air stream is cooled at a constant mixture pressure to a temperature below the dew point temperature, some condensation of water vapor can occur, and this principle is called as a dehumidification. Now, how I can dehumidify? That means, you have to cool this temperature below dew point temperature. In fact, we have deliberately discussed about how a dew is formed in our previous lecture, and with that concept we can use this particular concept to design a dehumidification processes. What a typical process dehumidification looks like is that we have a chamber. We can assume that there is a control volume sections, and this control volume sections has two part. One is a dehumidifier section, other is a heating sections. Basically what is the user requirement is something else, and that user requirement is at maybe at state 3, which is the user requirement, and moist air which is available may be at the inlet state. So, we have to design a system such that from the available state we have to bring it the state of the moist air to be changed to the user requirement state. So, one way that we have to do this thermodynamically, that we have to rely on this psychrometric charts. How I can design my dehumidification processes such that I can just fix them in the psychrometric charts, and if it is not possible to fix the psychrometric chart, then such a system is not possible. So, what we normally do is that for a given available stream, we can then locate that as a state 1, and for that state 1 we can say this is the if you look at for this particular system, for this state 1 which is for which we know omega and T 1, we can fix the state 1, and correspondingly if you go along this line, along same humidity ratio line, we will reach the saturation line which is the dew point for that situation. Now, what we have to do, that what this dehumidifier do, normally to do this dehumidification you have to remove water vapor. So, for that thing you have to use a cooling coil, and this air is allowed to interact this cooling coil. So, when that means this cooling coil we have to use such a way that when this air gets interact with this, then it will reach the dew point, and it will reach the dew point temperature. When the dew point temperature is reached, water vapors gets condensed and they come as a condensate, and the rest of the desired air they can go and leave the section 2. Now, in doing so, not necessarily in that process we will be able to achieve the humidity, but we cannot control the temperatures. So, then we have to do some kind of heating or cooling coil. So, here it has been heating coil has been used, so that temperature can be as desired, depending on the state 2 and depending on the final state we have to do that. So, one way is that to locate this is that means you have to bring down that state 1 to the saturation curve, where we will remove all the condensate in the form of water vapor, then subsequently we have to heat to reach the desired state. So, this is only possible way that we can achieve this dehumidification processes, and in this thing we also know that there is also a change in the temperatures, but other possibilities could be 1 to 3, but 1 to 3 we cannot directly draw in the psychrometric chart. So, 1 to 3 is not way, not the physical way of dealing with these processes. So, we have to go, because we cannot make the condensation unless and until we reach the saturation point. So, that is the reason we have to take this long path from 1 to 2, then again come back to the 3. This is how I have already explained the how the water gets condenses and the condensate gets cooled below this at this temperature T 2. And for this kind of systems we can use this similar way, this mass and energy balance equations. First, the mass balance equation for air, that remains same, water vapors it is mv2 plus m dot w is equal to mv1. So, the equation is a little bit, there is a, we can use this particular thing in a way that if the water gets out, so that is what it is a plus sign, but however, when you deal with these things, ultimately the negative sign will indicate that water will come down. So, in this way that we can frame this energy mass balance equation as well as this energy balance equation. Then moving further, this dehumidification processes, the other important aspect is that we have to locate these states 1 and 2 in the psychrometric chart, so that we can ensure the feasibility of a dehumidification processes. If all the states are not equilibrium states, the processes are indicated by dash lines. The next processes that comes as a humidification processes. So, humidification processes is just opposite to the dehumidification processes. Here we have to add water vapor into the moist air. So, this addition of water vapor into the moist air is possible by two means. One is if you can add in the form of a water vapor, other way is that we can add in the form of liquid. That means, you can spray as a liquid jet or you can spray as a steam jet. So, there are two ways in which we can add it. Now, when we are in state 1, that is moist air at state 1, that what happens when steam is added. So, when steam is added, obviously the humidity increases and of course, the temperature also increases. So, when a high temperature steam is injected, this dry bulb temperature increases. So, this ensures that addition of either water vapor or steam always increases humidity ratio, but when a steam is added, its temperature of air goes up, and this can be denoted in this psychrometric chart, that point 1 goes to point 2 in these directions with increase in the dry bulb temperatures. Other way is that if I add steam into this, then water into this moist air, the dry bulb temperature is going to drop. So, and when it drops, that means it is water is added and temperature drops. So, this is the very basic fundamental thing that we should know, that when a relative high temperature steam is injected, the dry bulb temperature is injected. If liquid water is injected, then it will lower the DBT. Now, another important aspect is evaporative. So, this is something like similar to adiabatic saturation processes. Where we require this evaporative cooling? Because cooling in hot and dry climates can be accomplished by evaporative cooling. Normally, evaporative cooling gives the advantage that when we have a very hot and dry climate, then evaporative cooling gives a better results. the very basic principle of evaporator cooler is to spray water. This is something like cooler you are using in our household applications, that it is a evaporative cooler to spray water into the air or forcing air to pass through a pad soaked in the water. Now, due to a lower humidity of moist air at state 1, the part of water injected gets evaporated, and because evaporation causes cooling, this is the fundamental principle. So, the energy transfer of for evaporation is provided by the air stream. So, the air leaves at a reduced temperatures, but at a higher humidity ratio. That means, humidity ratio can be increased, but temperature is lowered. And for this case also we can form steady state form of mass and energy balance equations, and all injected air is assumed to be evaporated into the moist air stream. Now, if you look at this particular domain, so what we have is a control volume where we have a soaked pad. Soaked pad means it contains it is a basically mixed with water, soaked with water, and air is allowed to pass through or is forced to pass through these things. Now, when it in this process when it is allowed to pass, then what happens? The temperature increases in this case. So, when the temperature increases, then what happens is, here temperature here drops. So, T2 is less than T1. So, dry bulb temperature drops. When the dry bulb temperature drops in the psychrometric chart, the process goes from 1 to 2 in this direction, and in this way if you can actually locate the state point and find the enthalpies, then we can see that enthalpy at state 2 is higher than that of state 1. Okay. Then this energy balance equation can be applied here as well. So, when we apply this energy balance equation, it has three entities. One is moist air that enters, water at TW, and moist air that leaves. So, moist air that leaves. So, we can write this energy balance equations, that the QCV plus m dot A into HA1 minus HA2, this is the air part, and this particular part is for water vapor, and this particular part is for water which is getting added. So, here T2 is less than T1 and omega 2 greater than omega 1. So, this is how we can write down these energy balance equations for evaporative cooling processes. The last part is the adiabatic mixing of two moist air stream. Theoretically possible that we can have a one stream, two stream or multiple streams of air which comes and they try to mix and they goes out. And in most of the cooling application or air conditioning application, there are only normally there are two moist air streams that comes from two different inlets, and they may be at different states MA1 and MA1 T1 omega 1, MA2 T2 omega 2. Now, when they come and mix, and finally after mixing they go as a single entity at a conditions MA3 T3 and omega 3. Such a systems you have to locate them in a psychrometric charts. To do that, what we have to find out? Mainly we have to find out the enthalpies which the moist air carrying. So, enthalpy is the very vital factor. So, state point 1 can be located based on the data available T1 omega 1, and state 2 can be located based on the data T2 omega 2. So, when we know the state 1, we can join this state 1 and 2, and obviously the state 3 will fall on this line, any point on this line. So, from this we can locate the enthalpy values, and finally we can find out what is the condition 3. Now, a point, very basic point is that why the point 3 will lie on this line. So, to prove that we have to rely on this mass balance and energy balance equations. So, mass balance equation we can write m dot A1 plus m dot A2 is equal to m dot A3, and that is for dry air, and for moist air we can introduce the humidity ratio omega, and which can correlate the mass of water vapor with mass of dry air. So, from then we can also do the mass balance equations for water vapor. When you do this, and we can finally land off a equation which involves the ratio of m dot a 1 by m dot a 2, which is nothing but equal to omega 3 minus omega 2 divided by omega 1 minus omega 3. So, this is not nothing but a linear relations. Similar way, another equations we can find out m dot a by m dot a 2 from this enthalpy equation also. So, this enthalpy equations here q dot C b, because it is adiabatic mixing. So, q dot C b is 0, w dot C b is 0. So, we can, so the rest of the things which are left with, that m dot a 1 H a 1 plus omega 1 H g 1, that is for the state 1, and this is for the state 2 m dot a 2 H a 2 plus omega 2 H g 2, and that is equal to m dot a 3 H a 3 omega 3 H g 3. So, when we do that omega 3 H g 3, there is a typo here. So, ultimately we can use these particular relations here, and we will find that the mass of air 1 and 2, they form a ratio with respect to this enthalpy values at different states, and this linear relation proves that the point 3 will always lie on this straight line. Okay. These are all about the different psychrometric processes and how different psychrometric properties that can be used for designing air conditioning systems. So, now we will discuss some of the numerical problems which is based on certain air conditioning processes that we discussed so far. So, the first one is nothing but your dehumidification processes. So, for this dehumidification processes, let me recall that we recall this figure, and to recall this figure, what we require now, locate the states of moist air in the psychrometric chart. So, that is the first step that we have to do. So, to do that, we must know that what are the things that we know. So, this typical dehumidification processes can be rewritten in this way, that we have a dehumidifier section, and we have a heating section, and we have a cooling coil, and through this cooling coil we have a container carrying condensate. So, what we know is that moist air that enters, it is interacting with this cooling coil. When it interacts with the cooling coil, the water vapors comes down as a condensate, and finally, the air that goes out, that in a heating section just to control the temperatures. So, you can locate the states as 1, that is state which is leaving 2, the condensate is 2, and the state that is leaving is 3. So, what is given? State 1, (30° centigrade 50% RH), dBT 50% RH. So, 30° centigrade dBT and 50% RH, we can roughly locate the state somewhere here, and for this we can actually find its values. One is H 1 is equal to 58 kilojoule per kg dry air, we can also find out omega 1 0.01333 kg per kg dry air So, we know this state and of course, we can find the specific volume. The specific volume we can find out something like 0.87 meter cube per kg dry air. This is 98786 kg dry air. So, once you know this, then we also the state 2. So, state 2 is nothing but the saturated air at 10 degree centigrades. So, for this, so at 10 degree centigrades saturated air, this value would be omega 2 0.0076 if you can draw the vertical kg per kg dry air, and this enthalpy value is close to 30. So, now we can first find out what is m dot A. M dot A we can find out, we know volume flow rate, that is V by specific volume. So, volume flow rate is 5 meter cube per second, specific volume is close to 0.86. So, this number will be roughly about 5.7 kg per second and it remains same, and then we can find out m dot V 1 is equal to m dot V 2 plus m dot W. So, we can write omega 1 m dot A is equal to omega 2 m dot A plus m dot W. So, from this we can say m dot W by m dot A is equal to omega 1 minus omega 2, and this m dot W, this value would be m dot W by m dot A is equal to 0.0057 kg by kg dry air. So, this is the rate at which the condensation takes place, and mass flow rate of dry air we already evaluated, that is first part. Second part, we say that what is the rate of condensation of water vapor, we can say 0.0057 kg of condensate that comes per kg of dry air, and third thing that we have to find out refrigerating capacity. So, refrigerating capacity we can write Q dot is equal to m dot A H 1 minus H 2. So, cooling load we can now calculate, m dot A is already known, 5.7 into H 1 is 58, H 2 is close to 30, so this means Q dot is 159.6 kilojoule per second, or Q dot is can be written as 159.6 divided by 3.52. So, that is 45.3 TR. So, these terms of refrigeration we can find out. So, this is the problem that we use for dehumidification processes. So, the very basic bottom line that with what we did, we locate the state points 1, state point 2. By locating the state points, we calculated the properties values, enthalpy, specific volume, then and use them in the calculations. The next problem is on a spray dehumidifier. So, this is again a spray humidifier, and here the data that is given, moist air which is given with dBT of 20 degree centigrade and WTBT of 9 degree centigrade enters the spray humidifier with a flow rate, and saturated vapor at 110 degree centigrade is injected to the mixture at a rate 60 kg per hour. So, we have to calculate humidity ratio and temperature of moist air at the exit of the stream. So, you can draw this simplified version of the problem that we have a situation in which moist air enters this control volume and state 1 dBT 22 degree centigrade, WBT 9 degree centigrade. Saturated water vapor at 100 degree centigrade. So, it is a steam. So, this is entered at 110 degree centigrade. So, to do this you have to use this steam table to calculate this property at 110 degree centigrade, and this is nothing but 60 kg per hour, and this moist air that enters 100 kg per minute m dot A, and what is leaving state we do not know, leaving state we do not know, we want to find out what is humidity ratio and what is temperature. So, we also have to find to enthalpy, because without enthalpy we cannot find the temperature. So, that is the state 2 and this is the state 3. So, the solution first we have to see the locate the point state 1, we go 22 degree centigrade dBT and 9 degree WBT 22 W. So, that if you look at here 22 degree dBT goes like this and 9 degree WBT, wherever it cuts 9 degree WBT, 9 degree WBT line is somewhere here. So, it cuts here. So, the point 1 is located and point 2 we do not know. So, point 1 is located. So, state 1 we can write dBT 22 degree, WBT 9 degree. So, this will give you omega 1 close to a value 0.002 kg per kg dry air, and also from this we can calculate the enthalpy. Enthalpy value will be close to 27 kilojoule kg dry air. Then we have state 3, because state 2 condition you do not know. So, state 3 is saturated water at 100 degree 110 degree centigrade. So, steam table will tell you what is its Hg value, gas phase, that is 2691.5 kilojoule per kg. Now, we can write this enthalpy equation H2 is equal to H1 plus omega 2 minus omega 1 into Hg 3, right. To calculate this, what we have to recall this equation, m dot A 1 is equal to m dot A 2 and omega 1 m dot A plus m dot steam is equal to omega 2 m dot A, steam is getting added. So, from this relation we can get a relation what is omega 2 is equal to omega 1 plus m dot steam divided by m dot A. So, steam rate you have given, so you can put the number here. So, omega 2 would be, omega 1 is already calculated 0.002 and m dot steam is 60 kg per hour. So, 60 by 3600 kg per second and m dot A is 100 by 60 kg per second. So, this will give you omega 2 about a number 0.012 kg by kg dry air. Okay. So, state 2 is located on this line 0.012. So, 0.012 line is this. Okay. So, state 2 will lie on this horizontal line which is 0.012, but exact location, for exact location we need another parameter which is unknown to us, but this can be find out because you know omega 2, we know H 1, we know Hg 3. So, we can find out H 2. H 2 is will be equal to 27.2, which is 27 plus omega 2 minus omega 1 0.012 minus 0.002 into 2691.5. So, this will be H 2 would be approximately 54.1, let us say 54 kilojoule per kg dry air. So, state 2 we can find, one is on this line wherever we get 54. So, 54 enthalpy, that means you have to go along the constant enthalpy line. So, along the constant enthalpy line, then roughly 52, 54 line will come here, it will intersect at this point. So, if you draw a vertical, so this number would be close to 25 degree centigrade. So, with respect to omega 2 0.012 kg per kg dry air and H 2 as 54 kilojoule per kg dry air. The psychrometric chart point 2 is located, initially point 1 is here, point 2 is here. So, T 2 will be approximately, we can say it is 25 degree centigrade. So, likewise, so that means you can see how easy if you can locate this point on the psychrometric chart. One thing I need to emphasize, these numbers may not be exactly these things, but it will give an approximate estimate when you look at the psychrometric chart. The third question is on evaporative cooler. This is also we studied today. So, in this evaporative cooler, the concept goes that the air is allowed to pass through a soaked pad in which the moisture gets added into this air, and by virtue of its the moist air exists from the evaporative cooler. So, very basic bottom line of philosophy of this evaporative cooler, that we have to rely on adiabatic saturation processes. Now, to locate this point, we have to think about remember how what is the wet bulb temperature at the end of the processes. Now, once you know the wet bulb temperature, because along this adiabatic process wet bulb temperature does not change. To do that, we have to first draw the simple system. We have some kind of soaked pad which is kept, which gives the water at state 3, moist air enters at state 1, leaves at state 2. So, entry state dBT 38 degree centigrade, RH 10%. So, 38 degree centigrade somewhere here, RH 10% is this point. So, the point 1 is located. So, point 1 is located, we can write state 1 omega 1 is equal to close to a value 0.004 kg by kg dry air. And for this we can find the specific volume. Specific volume also is required. We can say somewhere in this line 0.999, 0.85. So, small b a 1 could be 0.88 meter cube per kg dry air, 88. We can take approximately 0.88. Then m dot A we can calculate, that is equal to B 1 by B A 1. B 1 is given 120 by 60 divided by small b 1 0.88. So, this number would be 22.7 kg per second. Then m dot 1 we got, then what is equation fundamental, that equation you can use the state 3. State 3 is at state 3 we do not know. So, for the state 3 is water added at 21 degree centigrade. Then what equation you can think of, omega 2 would be equal to omega 1 plus m dot W by m dot A, and m dot W is equal to m dot A into omega 2 minus omega 1. So, m dot A you know 22.7, omega 2 0.012. Okay. So, to do that we have to go along this constant wet bulb temperature line till it we cross it at 21 degree centigrade. So, 21 degree centigrade means when you cross this we will have this number 0.012. So, 20, 10, 20, 21 degree centigrade. So, from this we can say this omega 2 is 0.012 minus omega 1 is 0.004. So, this m dot w we can find out 0.1816 kg per second. Then omega 2 at 0.012 kg dry air, WBT is equal to 21 degree centigrade. This will give phi would be close to 70%. So, state 2 will be here 0.012 line phi would be 70%. So, this is how we are going to locate the states 1 and 2 in the psychrometric chart, get the properties and then use them for to solve the problems. So, here we have attempted 3 problems, one on dehumidification processes, other is humidification processes, third is evaporative cooling processes. So, next class we will talk about similar problem on a adiabatic mixing process. So, with this I conclude this lecture for today. Thank you for your attention.